My name is Lorenz, and I will be talking about monitoring MEG measurements with MNE Scan today. So first, a quick introduction about myself. I started my PhD in 2015 with the Haueisen or Jens Haueisen group in Ilmenau at the Institute of Biomedical Engineering and Informatics. I grew up originally in Aachen and then ended up in Ilmenau to do my bachelor, master's, and also PhD. And then in 2015, when I started the PhD, I was able to spend the first 7 or 8 months with Yoshi Okada at the Boston Children's Hospital. And there I was responsible for implementing the new software for this new baby MEG device. And then in 2018, I came back to Boston to join Matti Hämäläinen's group here at the David Cohen MEG laboratory. And yeah, until today, I am here. And as John mentioned, I will be defending my thesis soon, and then I will start my postdoc here with Matti. Yeah, and for the ones who don't know me, I'm the right guy here on the right next to Shiraz and John in the picture. And my research interests are in real-time processing of MEG and EEG data. And in that scope, I'm currently maintaining and also one of the core developers of the open source MNE CPP project. So now people who are familiar with analyzing EEG and MEG data most likely have heard about MNE, and that there are a lot of projects like MNE Python, MNE C, MNE MATLAB. And why another MNE project? Why MNE CPP? In order to answer this question, just this quick slide about what MNE actually is. So MNE stands for Minimum Norm Estimates, which is a method developed by Matti Hämäläinen. Sometimes we also just refer to it as MEG and EEG. And MNE software comes in multiple flavors. So it all originated with Matti's MNE C implementation, and then we have these 3 packages now: MNE MATLAB, MNE Python, and MNE CPP, which are the largest ones. MNE Python was created by Alexander Grumford and is more focused on highly customizable analysis scripts, so fast prototypic scripting in Python, so very data scientific approaches, very data holistic approaches. Whereas MNE CPP, which was created by Christoph Dien, is more focused on real-time analysis and is implemented very hardware near, very acquisition near. So with C++, we interface a lot of the hardware and the devices, and also we focus more on graphical user interfaces and command line interfaces. Just as MNE Python and also MNE MATLAB, MNE CPP is open source, it is completely, as the name suggests, written in C++ and hosted on GitHub. It has 2 external dependencies, and here we are really trying to keep it to a low number of dependencies because we don't want to get into this maintenance hell and dependency hell. On the other side, and that is more downside of this, is of course we have to rewrite a lot of our stuff or the stuff we use from scratch. So one of the external dependencies we use is Qt. Qt is a GUI framework. Not only that, but also some other nice 3D visualization tools are implemented there. And then the second dependency we use is Eigen, which we use for matrix operations and linear algebra. MNE CPP is structured as a 2-layer architecture. So we have a library layer, which we can use via an API, and that library layer hosts all the hardcore methods like input output of data files, forward inverse modeling, visualization, pre-processing, and all of this is real-time capable. And on top of this library layer, we have the application layer, which then hosts different graphical user interfaces and also command line interfaces. And one of these GUIs is MNE Scan, and that's what I'm going to be talking about today. MNE Scan is our software to process data in real time. So what is real-time data processing to us in our project? We try to ensure that the data, which is flowing into MNE Scan, is being processed within a certain time constraint or time limit. So for example, if we get a data block every 100 milliseconds, we have to be able to process the whole data block in just under 100 milliseconds in order to stay real-time capable. And this processing of this data block can, for example, include filtering, visualization, source localization, connectivity estimation, all these things. And they need to be extremely fast in order to not, in order to cope with this real-time process or requirement. And why real-time data processing? So first of all, and maybe this is not the most apparent to outside users, is in MEG and also EEG, it's very important to monitor the ongoing recording because a lot of things can go wrong. So here we use real-time processing to give the study conductors during the measurement specific information about the current data quality, if the experimental setup is correct. And this way they can really check and also fix specific problems early on. And best example, you have your measurement setup and you think it's completely fine and everything is working okay. Then you measure the subject goes away, and in the post-analysis you see, oh, there's a big error and I forgot to, I don't know, activate this and that. So then you would have to get the subject back and do the whole recording again, which is very time consuming. And with real-time data processing, we can kind of prevent this. The next motivation is neurofeedback setups. For example, brain-computer interfaces, where we gather the data and process the data in real time. And then based on the current classification of the brain state, we create specific control mechanisms to, for example, steer external devices like a wheelchair and so on. Neurorehabilitation is also pretty back in neurofeedback for example, stroke rehabilitation. And then, of course, TMS, EEG, or now with ARPO's new device, TMS, MEG, closed loop scenarios, where you can really guide the stimulation, strength, location, and timing based on the ongoing measured EEG or MEG signals. And the third motivation is maybe a little bit far-fetched, but I think we are kind of scoping or looking towards it, that real-time data analysis at some point can give a faster diagnosis and more intuitive insight for example, clinical personnel. So they can really get a good impression of what's going on with the subject in real time. So MNE Scan has supported hardware, and for example, we can of course interface with MEG devices. This is something which Gabriel Motta, our software engineer, has been working on lately. We are able to, of course, interface with the MEG device here in Boston, and then also with the Baby MEG at BCH. And the Baby MEG you can see here on the right side. There you can see that we have MNE Scan running in front of this MSR, and the clinical personnel and the study conductors can use this to monitor the measurement. And here on the bottom part, you can see that it's pretty small, the Baby MEG, so we can scan children up to 2 or 3 years. Yeah. And EEG devices, we can also interface with those. We have the lab streaming layer, which is an independent community project, which we can interface with, and then some other devices as well. And lately, we also tried to integrate TMS devices. This is also done in a separate project called MAG-CPP, but we have a plugin in MNE Scan which can use and interface with these MAG-STIM devices. So this is what the MNE Scan GUI looks like for a normal measurement here at Martinos. On the left side, you have the plugin scene where you can create your own customizable pipeline. So you have sensor plugins which you can connect to all sorts of different devices, and then they pipe the data through your pipeline through so-called algorithm plugins, which can then, for example, filter, average your data, compute the covariance, do source localization, and so on. The real-time data stream is visible here at this signal viewer. So for every, for example, for the raw data stream, but also the filtered one, you can see the data in real time and interact with it. The 3D view shows you the real-time source localization, the function connectivity networks, and also the position of the subject's head relative to the sensors. And lastly, you have the average view, where you can see if you have a trigger-based measurement where you can see the different trials averaged together in form of a butterfly plot, but also as a 2D layout plot. So during a measurement, this would, I hope this is somehow you can see this. So this is a real measurement or a recording of a real measurement. You can scale and interact with the raw data view. So you can change the amount of data being displayed, how many channels are being displayed. You can activate trigger detection, so you can really see how and where your triggers are coming in. You can activate signal space projections, which is a noise reduction technique which we use in MEG a lot. You can, of course, filter the data, so frequency filtering is an option. You can design your own filters on the fly in MNE Scan, so you don't have to import that. Then the real-time averaging looks like this. Here you have your butterfly plot, and this is the 2D layout plot where you can see all the different triggers. So also multiple trigger types are supported on top of each other or superimposed to each other for each gradiometer and magnetometer channel. Yeah, and then of course you can scale them and interact with them. And here you can also select different groups, so you really have an idea of what's going on where in the measurement and in the measurements channels. Next thing is you can see or you can monitor the head movements of the subject. So in MEG we have so-called HBI coils, which are fixed to the head, run at different frequencies, very high frequencies. So in this case, they start at 154 Hertz. And this was something which Ruben Dörfel worked on while he was here. And you can see that the head is moving from the left to the right. This is exactly what we asked the subject to do. And with this, you can really see if the subject is still in a good position for the sensors. This is specifically important when you, for example, measure children, because they usually don't want to hold still. Also, it is important to know the position of the subject relative to the sensors in order to change or to update the forward solution and then the subsequent source localization process. This is also very important. Yes, speaking of source localization, this is the real-time clustered MNE, which was built or created by Christoph Dien. We can see here on the right side that on the average data which we received, which is based on a moving average, we can calculate the MNE solution and then plot this over time on the cortical mantle. So here we plot every single sample. That's why it's flashing over and over again. But you can, of course, also just see, for example, the N100 component, 150 millisecond component as well. This is also possible. And then based on the source localization or the localized source activity, we can calculate all-to-all connectivity networks, functional connectivity networks. So here you can see a coherence-based functional connectivity network for the localization results I showed you just before this slide. So this is all sample data. I computed this yesterday, and I mimicked a real-time data session with just streaming data, which is already pre-recorded. And you can see with incoming number of trials, because this is a connectivity network over trials, you can see that there is a clear network building and creating in the left visual cortex. And this is most likely just due to field spread. But yeah, so this is, we can do this in real time as well. And maybe also important to note here is that you can see and you can look at this in real time, but of course the results are there, which can then be piped to subsequent processing plugins. So you could, for example, now do, I don't know, a classification based on the source level connectivity networks, if you want to. Then maybe how can you use MNE Scan at Martinos? So MNE Scan will be installed once we are all back in the lab on a separate computer in the MEG lab. You can also run it on your own computer. We have the binaries available on our website. It runs on Mac OS, Linux, Windows, and actually the whole MNE CPP project is cross-platform, so you can run anything from MNE CPP on all of your devices. And what was really important to note is that MNE Scan is passive. So if you let MNE Scan listen into or receive data from your MEG measurement, it is passive. I mean, it runs alongside the FDA-approved software by the vendor, by the VectorView or the MEG today, it's called. And that is very important because this way it does not interfere with the actual measurement session and you are safe. So of course, MNE Scan is in a development status, so it can crash sometimes. And you don't have to be afraid of that because your actual measurement would still be going on with the vendor approved or FDA approved software. And yeah, if you're interested in using MNE Scan in your measurements to just, for example, monitor your data quality, but also if you think about new experimental setups, please do get in touch with us. What's next? So for MNE Scan, we are really eyeing at new clinical devices. So we right now have support for one clinical EEG device, which is the Natus. Mostly all the EEG amplifiers we work with are all research-oriented, but in big clinics like MGH, Cleveland, and then the epilepsy monitoring units, they don't use these research-oriented EEG amplifiers. They all use mostly neon codon and Natus. And Natus we already have in our device repertoire, and we're currently trying to include neon codon devices as well. And this is a process we are doing at Martinos and at UT Health together with John Borcher's group. Next to the clinical devices, we're also concentrating on getting the MEG TMS device into MNE Scan, because I think this is something we can really, where we can really use MNE Scan's real-time functionalities to guide the stimulation. And in general, TMS EEG closed-loop stimulation is also something which our colleagues from the TU Ilmenau are currently looking at. So they want to guide the location strength and the timing of the stimulation based on the current brain states or the incoming data in MNE Scan. And with some other collaborators from BCH, we are working on monitoring ECOG and SEEG, so invasive implantations of electrodes. They currently have a very interesting setup there. So during their surgical intervention, when they place or implant these electrodes, they analyze the data, store the data on a network drive, send it to a high performance computer. From there are some people analyzing the data. That takes about 20 minutes. They prepare a slide in PowerPoint, print it out, run over to a different building, or to the building where actually the surgical process is happening. And then the doctor or the surgeon looks at the data and decides, okay, maybe I have placed it a little bit. And this process takes roughly 20 to 30 minutes. And they call this real time for them. And they were, when we showed them what we can do with the software, they were very amazed. And we are now trying to get their workflow in MNE Scan as well. So for MNE CPP, next to MNE Scan, we also are currently working on an offline version of MNE Scan, or an offline version which we can give to the users, and that will be called, or it's called MNE Analyze. And what we have witnessed so far is that it's very difficult to get the software into the clinical environments because the IT there is just so strict. So what we are trying to do right now is to port most of the MNE Analyze, so the offline analysis software, into WebAssembly, which lets us run our software inside of the browser, of any web browser, so Google, Chrome, Mozilla, and so on. So this is also something we are currently looking at. And in the end, MNE CPP is open source, so and we do only depend on two external dependencies, meaning that we have a wide variety of different topics where people can work on. So if you want to get involved and are interested in general MEG analysis, source localization, real-time processing, C++, basics, or advanced C++, 3D visualization, GUI programming, don't hesitate, and please get in touch. And yeah, there's a website, mnecpp.org, and there you can find all the necessary information. The team, so we have 4 PIs, Matti, Jens, Joshua, and John. And then here are some code contributors in alphabetical order, which already contributed to the current state of MNE CPP and MNE Scan. With this slide, yeah, the end of my talk. I hope you enjoyed it, and yeah, have a nice weekend and pause.